there. In this video, we will explore two concepts, the formation of a double bond and the resonance structure. Now let's go back to the carbon atom for a minute, and we'll use the example of a carbon atom to explore the hybridization and the formation of single, double, and triple bonds. So the electron configuration for carbon atom, as you know, is 1s2, 2s2, and 2p2. And we're going to pull out the 4 valence electrons and put it aside for a minute. And I want to just draw the empty orbitals, and this is the 2s orbital, and this is the 3p orbitals in the second energy level. So there are 3 ways in which the s and the p can hybridize or mix. The s and p can hybridize with 2p unhybridized, or you can have sp2, meaning 1s and 2p orbitals will hybridize, leaving one of the p's not hybridized, or all of them can hybridize, sp3. And in the case of carbon, it would form 4 bonds, and I'm going to try and show this as a tetrahedral shape. But going back to sp hybridization, it will form a total of 2 hybrid orbitals, and this is our 2 pure, what I will call pure p orbitals, unhybridized. Let's imagine 2 carbon atoms that underwent the sp hybridization. So here's one and here's the other one. So this is the sp hybridization, and I'm going to write a little sigma bond here to show you that this is the sigma bond. With the other sp hybrid orbital overlaps to form a hydrogen bond, and the same thing happens over here. Okay, so we've shown the 2 sigma bonds here, and that's the electrons from each of the carbons. Now I want to discuss the p orbital. Here's the p orbital from one carbon, and here's the p orbital from the other carbon, with 1 electron here and 1 electron here. And what really happens is that the p's will overlap to form a second bond. And what we have is, this was our original sigma bond between the 2 carbon atoms. And I'm just going to put this hydrogen here to show what happened to the other sigma bond from the hybrid orbitals. And the second bond that formed was the pi bond, and this was due to the p overlap. The p orbital that did not hybridize. And same thing with the second p orbital here, they will overlap as well and form another pi bond here. So what we have is a triple bond. And we'll just show these hydrogens here. I now want to talk about the sp2 hybridization. And here, the hybrid orbital is a total of 3. So this carbon is capable of 3 sigma bonds, and the 1p that is pure p remains unhybridized. Now let's imagine a carbon with sp2 hybridization forming a sigma bond with another carbon which underwent the same hybridization, and this time each of the carbons will form 2 sigma bonds with something else. Let's just say hydrogen again. Okay. Now remember that there is a p orbital here on each carbon, which, like before, will overlap to form a pi bond. And what we have is our original strong sigma bond and 1 pi bond here. And of course, there's other 2 sigma bonds will be used to attach to hydrogen in my example here. So this is the story of how a double bond is formed. I find that students get very confused about this, so I'm going to repeat myself. The s orbital can combine with only one of the p orbitals to form a hybrid orbital, and the hybrid orbital is what will form the sigma bond. So here, this is a sigma bond and this is a sigma bond. These two p orbitals, which did not take part in the hybridization, they will overlap with another carbon. Bear in mind, this p orbital, the unhybridized p orbital, is present in both the carbons, and so is the hybridized sp orbital. So from each carbon, the unhybridized p orbital will overlap to form two pi bonds. When the s orbital combines with two of the p orbitals, we have a total of 3 sigma bonds and only one p orbital available for the pi bonding. So here we have 3 sigma bonds. One of them is used to attach to another carbon, and of course this carbon also underwent the same hybridization, so it contributed its sp2 sigma bonds, and they're connected, and the other 2 sigma bonds was used to attach to the hydrogen, similarly with this carbon. So we have a carbon-carbon double bond and carbon-carbon triple bond. I now want to consider the resonance structure. When there are 2 or more possibilities of a double bond, from your Lewis dot diagram, you must show all the possibilities with a double-headed arrow in between each option. Let me show you an example. Consider ozone, O3. Using our 4-step system, we will predict that our 3 oxygen has a total of 18 electrons, and we will predict a bond which may be something like this, where you take 4 electrons off and you are left with 14 electrons. Let's say this oxygen, as it stands, will need 6 electrons to complete the octet. This oxygen will need 4, and this oxygen will need 6, and you see that we don't have enough electrons. So if you were to put the electrons, you will find that you're short of electrons. So you've used up 12 and 13, 14 here, and you know that the oxygen in the middle still needs 2 more electrons. So what really happens is that one of these electrons will probably want to go out there and share it, and you end up with a double bond there with 2 electrons here, and this oxygen stays as 2 electrons, and you have an octet in each one. Let's do an electron count: 2, 4, 6, 8, 10, 12, 14, 16, 18, and we're good. The question is, what is stopping this oxygen from keeping all of its electrons and this oxygen sharing? Actually nothing. So that you can have it both ways. So with the central atom, and their double bond is over here, and this remains as a single bond, and this one will have 6 electrons, and this oxygen will now have only 2 pairs of valence electrons, with the central atom having that pair of valence electrons. And this is what a resonance is. Let's try NO3 1-. If you like, if you feel comfortable, you can pause the video and do it on your own and then run the video. Or you can watch me do this. So nitrogen, we know, has 5 electrons. 3 oxygen, we know, has 18 electrons. And that charge here will contribute to 1 electron. So we now have a total of 24 electrons. So let's put the nitrogen, which is the least electronegative, in the middle. And let's place the oxygen. Let's evenly space it out and connect them before they fly off with 6 electrons. Each bond has 2 electrons. 2 electrons here and 2 electrons here. So we have 6 electrons. So what we have left is 18 electrons. Now let's go ahead and assess the situation. Each one of these oxygens would need 6 electrons to complete the octet, and the nitrogen would need 2. So that gives us a total of 20 electrons. And you know we don't have 20. So immediately we can start putting some double bonds somewhere. So let's just, for the sake of argument, do this. Let's give it 6 electrons. Let's give this one 6 electrons. And let's give this oxygen 6 electrons. And we know this is not going to happen because nitrogen doesn't have the 6 electrons. So what now? Either this pair will form a double bond, or this pair would form a double bond, or this pair could come here and form a double bond. So what do we have is 3 possibilities. Let's just try one of them. Nitrogen forming a double bond with this oxygen here, and we now have only 2 pairs of electrons. And this is a single bond, and this is a single bond. Nitrogen now has 8, and these electrons stay right where they are. The other possibility would be a double bond here with these 2 single, and we really want to put the negative charge. We must never forget the negative charge here, and that is in resonance with this possibility here. And I'm going to put the third one out here, and that would be in resonance with this possibility of a double bond here. So, of course, you must show your non-bonding electrons. So I'm going to move this out a little bit so I have some space. And here we go. Again, square bracket, minus charge. And what happens is it turns out that the NO3 1-, the nitrate, exists in all 3 possibilities. And they're spent 1/3 of its time in each of these possibilities. And we say that NO3 resonates from one structure to another to another. So this is what a resonance structure is. I'd like you to pause the video and try this. Okay, so you know that carbon has 4 valence electrons, and you know that oxygen has 18 valence electrons, 6 each, 6 3s are 18, and there is a charge, so you have to add 2 electrons, and we have 24 electrons altogether. Okay, let's put the carbon in the central atom here. It's least electronegative, and let's place the 3 oxygens around it and connect them with 2 electrons each. So I've already used 6 electrons, and I now have 18 electrons left. And in looking at what I've done, it looks like carbon will need 2, and each of the oxygens will need 6. 6 3s are 18 plus 2 is 20, and I know I won't have enough. If I gave the oxygen the complete octet, and you and I both know that this is not going to happen because the carbon is deficient, but you can see that you can either form a double bond here or here or here. So what we actually have is 3 possibilities resonating from one possibility to another, and this is how we write it. Okay, how about a little test? I want you to pause the video, get yourself a sheet of paper and pencil, and see if you can do this by yourself. All right, welcome back. Now let's see how you did. Now, I will put the answers up. Number 1, 3 nitrogen has 15 electrons and the charge was 1. So we have altogether 16 electrons. And nitrogen, nitrogen, nitrogen. Let's connect. And you can do a double bond on each nitrogen and place electrons here, and that would resonate or will be in resonance with a triple bond here. And that's in resonance with triple bond on the other side. I'll just put one negative charge out here. I think that's quite acceptable. The second one was NO2 minus. So we have a total of nitrogen contributing 5 valence electrons. Both the oxygens would contribute 12, and the charge contributing 1, and we have 18 electrons to play with. Okay, and the final answer is... The next question was HCO2 1 minus, and we are told that hydrogen is attached to the carbon. So we've got some clue there. So we want to put carbon here, and hydrogen is attached to the carbon, and there's the 2 oxygens attached to the carbon as well. We have 1 electron contributing from here, 4 here, 12 here, and the charge gives a 1. So 12, 13, 14, 15, 16, 17, 18 electrons all together, and I basically used 6, so I now have 12 electrons. Remember that hydrogen violates the octet rule. You should know this from the previous video that hydrogen only has one s orbital. It doesn't even have a p orbital to hybridize with, so there is no way hydrogen could expand its octet to 2, let alone 8. So we only need to worry about the oxygen. It'll need 6, this will need 6, and the carbon will need 2, and this gives me a total of 12, 14 electrons. I can immediately see that it's just not going to be enough. So if this oxygen took all it needed, it'll have to swing out and share, or similarly this oxygen will have to contribute to share. So we now have ourselves a situation where we could have either a double bond here, or I think I want to do my charge before I forget, or you can have a double bond here and a single bond there with a charge. And that's the resonance structure. I hope you got this. And of course we need to put our little electrons. Question 4 is very interesting. It's HBr04. And you are told that H is attached to oxygen, oxygen is attached to bromine, and the 3 oxygens are attached to bromine separately. So put bromine in the middle, and H is actually attached to the oxygen, so that's the situation there, and 3 other oxygen is attached to the bromine. Now we have 7 electrons, 1 electron, and 24 here, 32 electrons altogether. 32 electrons altogether. I actually used 2, 4, 6, 8, 10. So I have 22. And it looks like this oxygen here would want 4, 6, 6, 6. And you might think that bromine is all happy. It has 8 electrons. 6 3s are 18, 19, 20, 21, 22. So this pretty much looks like it's okay. But I want you to understand that bromine is in the 4th energy level. and can hybridize, and can hybridize with D and even F to expand the orbital to beyond 8. There's nothing stopping these electrons to swing out here, or these electrons to swing out here, or these electrons to swing out here, and we can actually have a lot of resonance. I'm only going to show one, and I just want to tell you that there would be 3 equivalents here. Now, in my next video, I will talk about the formal charges, and it is possible to calculate the formal charges of each of these atoms and predict whether your suggested scenario or your diagram of the molecule is reasonable. Last one, question 5. If you remember the question, it was NO2F, and you were told that the nitrogen is the central atom. So nitrogen will contribute 5 electrons, 2 oxygen will contribute 12 electrons altogether. Fluorine will contribute 7, and we have 24 electrons altogether. Let's put the nitrogen in the middle. It's the least electronegative, and it makes sense to put nitrogen in the middle and arrange the other atoms and immediately connect them. And I've used 6 electrons to connect them. So I now have 18 electrons left. And if you look at what we need 6 here, 6 here, 6 here, and 2 here. 6 3s are 18, 19, 20. I know I'm short, so I have to make some double bonds here. Let me satisfy the fluorine. The rule is that they will only make one bond. If you looked at the electron configuration and the hybridization of fluorine, you'll find that the fluorine will only make one bond. Oxygen can make 2 bonds. So then the oxygen will be only too happy to share, or this oxygen will be only too happy to share. So we have ourselves a resonance structure. Okay, very good. Thanks for listening. I will see you in my next video. Goodbye.